So let's get started with matrices, and one of the simplest meanings of a matrix is a table of data. So imagine we have some table like students, we have first student, second student, and we measure some parameters like age and height, right? And let's fill the table, like first student is 22, second 21, and height is 180 and 170, right? And we can represent this table as a matrix. We just need to rewrite all those parameters as zero, so like 22, 180, 21, 170. So the main idea is that the first row is our observations, so our students, like first student, second student. And each column is our feature, like first column is age and second column is height. And the shape of this matrix is 2 by 2. It means that 2 rows and 2 columns. Please notice that in this notation, row index is first and column index is second, okay? So we can rewrite this to the general form, like matrix A can be represented as A11, A12, so it means like first row, first element, first column, first row, second column, first row, third column, and so on to the first row, column number n, right? And for second row, first column, and so on to the second row, column number n, and so on for the m rows. So we have like m rows and one column to the m rows and n columns. So the shape of this matrix is m by n, right? Okay. And as it shows, this matrix can represent the table, and it also can store many vectors stuck together. Like imagine we have vector x1, which is equal to like 1, 2, 3, vector x2 equal to 2, 4, 6. And we can stack this vector together to some one structure, one matrix x, which is equal just to 1, 2, 3, 2, 4, 6. Okay. And let's move to some basic matrix operations. Okay, so first of all, it's matrix addition and subtraction. So to add or subtract one matrix to another, we need just to add each component individually. So like imagine a matrix 1, 2, 3, 4 plus matrix 1, 2, 3, 4. Then we have some results like 2, 4, 6, 8, right? And the same with subtraction. And elements can be negative as well. It's not a problem. But the main point is the rule that the shape of this matrices A and B must be the same, because like imagine we have 3 rows, like 5, 6 in second matrix, and we just don't have any elements in matrix A, which we can sum up with these 2 elements, right? So we need to have the same dimension. Okay, and we can multiply matrix with a scalar. So if we need to write like 2a, multiply matrix A by 2, we just need to multiply each element of this matrix by 2. So it looks like 2, 1, 2, 3, 4. So we get a matrix 2, 4, 6, 8. Okay. Well, and sometimes for future matrix multiplication operations, we need to have proper shape of matrices, and sometimes we need to change the shape, and we have some operation called transpose, which means that we need to take like just to flip rows and columns of matrix. So if matrix A is equal to 1, 2, 1, 2, 3, 4, 5, 6, and then this transpose version is equal to, we need to take just first row, 1, 2, 3, and insert it to the first column. So 1, 2, 3. Then we take second row, 4, 5, 6, and insert to the second column. So 4, 5, 6. So it's our transpose version. Okay. And as I mentioned, sometimes we need to multiply vectors, and in some cases you can see some literature, you can see that we write vectors x, like x1 transpose. So we just take vector 1, 2, 3 and make it vector or matrix column instead of matrix row. So it will be like just 1, 2, 3. And we do that to have proper matrix multiplication. I will show it a little bit later, okay? Also, sometimes after matrix multiplication, for example, when we multiply matrix by inverse matrix, which we'll skip in this case, we can get 1. So when we but in matrix spaces, we can just have some element equal to 1. We need to have a matrix with corresponding shape. So we use something called identity matrix for that. It's written as letter I and have zeros and ones. So we use number 1 in main diagonal and zeros in any other place. Okay, and the main rule is that any matrix multiplied by this identity matrix will be the same, right? So it's equal to multiplication by number 1. Well, so let's move forward. Matrix multiplication, and it's our main operation. So suppose we have matrix A with shape M by N and matrix B with shape N by P. So matrix multiplication creates matrix of shape M by P, like that. And to multiply them, the number of columns of matrix A and N must be equal to the number of rows of matrix B. Okay, but why so? So let's see how matrix multiplication works on example. So imagine how matrix A, like square matrix A11, A12, A21, A22, and we multiply it by matrix B, B11, B12, B21, and B22. Okay, so to multiply the matrix, we already know that the final shape is M by P. So the shape of matrix A is 2 by 2, and same for matrix B. So the final output is matrix 2 by 2 again, okay? And so it means we have 4 elements. And to compute first element, we need to take the first row of the matrix AB, so it's like A1 and A2, and multiply it by a first column of matrix B. So it's A1, we have like dot product. A11 multiplied by B11 plus A12 multiplied by B21. Okay, and the second element is the same. We take this first row but multiply it by with second column. So we have A11 multiplied by B12 plus A12 multiplied by B22. Okay, after that, we move to the second row. So we take row number 2 and multiply again with first column and after that second column. So we have A21 B11 plus A22 B21, and second element A21 multiplied by B12 plus A21 or A22 multiplied by B22. Okay, so that's the main rule of multiplication. So we just multiply each row with each column, and that's why we need to have equal number of columns in the first row, in the first matrix, and rows in the second matrix. Okay, and like I can explain in another way. Like imagine we have, so we multiply row I of matrix A, so we have dot production with column J of matrix B, right? So it's like vector dot product, and we know that to multiply two vectors, to have dot product of two vectors, we need to have same dimensionality. Like we cannot multiply two-dimensional vector with three-dimensional vector, right? And same is here. So what is the len of vector of row I? We know that in this example, row is A11 and A12, right? And the line of this row is just two elements, so 2 columns, right? So 2 elements, and the line is equal to 2. And same with columns. We have columns in matrix B like B11 and B21, so it's 2 elements. So the line is equal to 2, and only in this case we can multiply these matrices, right? If we have like 3 elements in matrix B, 3, 1, for example, right? Then we cannot multiply these two matrices because we cannot multiply vector with len 2 with vector with len 3. Okay, hope it makes sense. And there is one important rule here. So matrix multiplication is usually not commutative. So it means that A multiplied by B is not equal to B multiplied by A. I mean, there are some examples when it can be equal, but usually it's not. And imagine some example, like we have, as I wrote before, A with shape m by n and B with shape n by p, right? So the output shape is m by p. And the rule is n must be equal to n, right? But if we multiply B by A, then we have n by p, m by n, and then we know that the output shape is n by n, so it's square matrix. It's completely different from the previous example, right? N by n, and to be able to multiply them, we must have p equal to m. You can take just example of A equal to 1, 2, 3, 4, and B equal to 5, 6, 7, 8, and just you can test it by yourself and multiply them in both directions. And there are a lot of applications of matrices, and we can, for example, imagine that matrix is a compact way, useful way to transform many vectors at once. So imagine we need to scale the vector, the like 100 of vectors, and instead of scaling each by some number, we can just multiply. We can just create some matrix of these vectors. Like let's create matrix 1, 2, 3, 1, 4, 5, and each column of this vector, of this matrix, is a vector. So first column 1, 1 is xy, x1, second column is x2, and third column is x3, okay? Or 3, 5, sorry. And now we have matrix A 2, 0, 0, 3. And if we multiply, so one important thing to mention, as we discussed, matrix multiplication is not commutative, so we need to specify from which side we multiply the matrix. So in this case, I multiply the matrix X from the left side. So I write it like that, okay? And if I do so, let's calculate this. So we have like 2, 0, 0, 3 multiplied by 1, 2, 3, 1, 4, 5. And the output is equal to what? We multiplied 2, 0 by 1, 1. So it's 2, then 2, 0 by 2, 4. So it's 4. 2, 0 by 3, 5. So it's 6. And the same with the second column. So it's 3, like 0 multiplied by 1 plus 3 multiplied by 1. Then 0 multiplied by 2 plus 3 multiplied by 4. So it's 12 and 15. Okay? And initial vector was 1, 2, 3, 1, 4, 5. Okay? And as you can see, this multiplication with these elements of matrix just scales the first coordinate. Like we have vector columns, right? So there are 3 independent vectors, and first row is our first coordinate, like x, and second column is y, like second coordinate, right? And this multiplication just scales the first coordinate, x, by 2, and second coordinate by 3, right? So it's just scaling transformation. Hope it makes some sense. So with this we can like scale a lot of vectors just with one multiplication operation. Okay, and one another example of transformation can be rotation. So imagine we wanna not just to scale but to rotate as a vector. So let's draw this formula for better understanding, because the matrix can be hard to understand the elements of this matrix. So if we have some vector A and with coordinates like x and y, and angle between A and x-axis alpha, and after that we rotate this vector by some angle beta and got new new vector with coordinates x prime and y prime, then we can derive these coordinates from each vector. So from the first vector, we know that this line is our y and this projection is x. So we can derive that, we know that cosine of alpha is equal to the x divided by the length of this vector. So let the length be equal to r, okay, divided by r. And we suppose that this transformation, rotation, doesn't change the line of the vector, okay? So cosine is equal to that, and sine is equal to opposite, so it's equal to y divided by r, okay? And so we can get each coordinate, like y is equal to r multiplied by sine of alpha and x is equal to r times cosine alpha, okay? And we can do the same for a new vector, x prime and y prime, so it's r. For x, it's cosine alpha, but we have new angle, so plus beta. And same with y, so we have sine alpha plus some displacement in angle, so it's beta, okay? Well, and we know from the trigonometry that cosine of alpha plus beta from sum of some angles is equal to the cosine of first angle multiplied by cosine of second angle minus sine of first angle times sine of second angle. And same with sine formula, when we have sine of sum of angles, we have cosine of first times sine of second plus sine of first cosine of second. And now we can put these formulas to the second table, second system. So x prime is equal to r times cosine alpha plus cosine beta minus r sine alpha sine beta. And same for y prime, which is equal to r cosine alpha sine beta plus sine r sine alpha plus cosine beta. Okay, and as you can see, these terms like r cosine and r sine are equivalents of our y and x from the first system, right? So we can replace, and in result we have like x prime is equal to just x cosine beta minus y sine beta, and y prime is equal to x sine beta plus y sine cosine beta. Okay, and now we can represent this system of equations as a matrix. So we can write that x and prime and y prime is a column matrix with one column, which is equal to, now we need to write the coefficients before variables, so it's cosine beta minus sine beta and sine beta and cosine beta, right? And multiply these coefficients with our variables, so x and y. So this matrix of cosines and sines is called rotation matrix for two-dimensional plane, and it rotates the vector, right? So imagine we have angle beta is equal to 90 degrees, so we want to rotate some vector 90 degrees. So the rotation matrix is equal to, just cosine of 90 is equal to 0, minus 1, 1, 0. So if we multiply every vector with this matrix, we will rotate this vector by 90 degrees, okay? So when we multiply some vector with this matrix, with some vector, column vector like x and y, with this matrix, we rotate this vector counterclockwise, so in like this direction, with 90 degree, okay? So if we have some vector like x is equal to 1, 0, so like column vector, let's build this some plot. So this vector, it looks like that. And we multiply this vector by this relation matrix, like on the left side, so 0, minus 1, 1, 0, multiplied by x, 1, 0, 0, 1. So in result, we have row multiplied by column, so it's 0 plus 0, so it's 0, and 1 multiplied by 1 plus 0 times 0, so it's 1, okay? So we have new vector like z, 1 on y coordinate. So we rotated this vector by 90 degrees, okay? So that's it. See you next time.